Good afternoon, this is Schweitzer, and doing a video here on one of our first looks at significant digits. Now, just a disclaimer here, I'm not exactly sure how everyone teaches significant figures, and it may vary some if you're not a student of mine, with maybe how your teacher teaches this, and there's different ways to teach this, but this is just one way that I have done this that tends to treat everything pretty logically and work pretty easily. So there's a couple things here that I might want to sort of discuss. First of all, when we measure a number, anytime a number comes across on a sheet of paper or anything, that number, whether it's 205, let's say decimal, that this particular number had to be measured. Either had to be measured or with a tool, or this number had to be counted, physically, manually counted, and therefore this would be basically an exact number. We'll take a moment to discuss the idea between a measured value and a counted or an exact value. So a measured value requires a tool which has inherent error. You cannot have an exact number, not exact. So every single tool has error, therefore every single measurement has error. At some point in time, you are going to be running out of the tool's usefulness, and then there's numbers that can't be measured. An exact value would be like 5 cats. This is a pretty much solid number. I mean, you count, there's 5 there. There's no errors, no ambiguity to this. One way that I would sort of describe this is that if you have a number, let's say 205, any number that for that matter, your tool is kind of like an eyeball looking down this number, and it looks down the number, and the farther we look, the more accurate the value is. So a number that can see, a tool that can see to the 10th spot would have a certain level of accuracy. Another tool might be able to see the 100th spot, and again your thousands and so on and so forth. But eventually every tool runs into a roadblock where it can no longer see anymore. There are still numbers here, we just can't see them. Every time we look at a number, we should realize that this number loses accuracy right here, as opposed to 205.0 loses accuracy here. As soon as the number stops, basically the tool has ceased to see anything beyond that point. Sometimes I put a little frowny face here and a smiley face here. I mean, we know these numbers, but we don't know these ones. Now, an exact value, which might entail, let's say, 5 cats. This would be 5, and I could put 0, 0, 0, 0, 0, and go on. It's always going to be good. There is no drop-off in my accuracy. So we often refer to this lengthy list of infinite number of zeros as basically being infinite significant digits, or significant figures, often referred to as sigfigs. Now, this is the first time we've talked about this idea of a significant figure. One quick note here. Again, this is something that may not be seen everywhere, because it's a rule that really, I don't know if it's ever really used, but other than this area, is that I call this the decimal rule. And basically we're looking at, how do we know if a particular value is an exact value? Well, a decimal rule, this is where I got from where I learned it, and I haven't really seen it too many other places, but a rule that's not very commonly followed, but is if there's no decimal, generally means that no decimal generally means exact. So, but because it's so it purely isn't followed all that well, and maybe isn't a rule that many people have heard of, we definitely want to use our units to clarify. So anytime I look at a particular value, and that's just so you know, if I have 520 cats, okay, I would say, okay, well, first of all, this thing here does not have a decimal, but this is a whole item, so likely this particular item could be exactly 520 cats. Again, if someone says 500 cats, you don't know if they're estimating at 500 cats or if there is exactly 500 cats. But at that point, I would sort of use my judgment and say, okay, well, if there's no decimal, it would be exactly 500 cats. But if it's 500 decimal cats, then it might be a measured estimated value of 500 cats. So the decimal rule, not the most highly followed rule, but just so you know where I'm coming from when I look at a few problems. If I say we have 500 meters, now a meter is not something that can ever be exact. I cannot have exactly 500 meters. Now I can, however, have 500 meter sticks, okay? I can order exactly 500 meter sticks, but not all the meter sticks are exactly 1 meter. They have some error involved in them. So in this case, again, emphasize the difference between an exact value and a measured value. You can have exactly 500 meter sticks, but you can not have exactly 500 meters. All right. Now again, just to get this idea of a significant digit. Okay. So essentially, I'm looking at a number, like say 205.000, and I said to you, okay, this tool is staring down this number, and it says, okay, well, where do I lose? Actually, I lose actually right here, and everything beyond that is no good. So these are the ones that I do not know, and these are the ones that I do know. So these would be significant. If you want to put it in terms of maybe a definition, I would say a significant digit is something that, one, is a number that has a value. All right. So kids, just because it's not significant doesn't mean it's not important. But a number that has a value, you might say, well, that's odd. Why wouldn't all numbers have values? Well, we'll see some examples where maybe they don't have a value. And the other aspect is, okay, a number where that value is known. Okay? Now, for significant digits, to be significant, has to have a value, and that value must be known. Now, just so you know, number 1 through 9 are all significant. I'm going to say sigfigs. For example, a 5. A 5 is significant. It is a number that is between 6 and 4. So 5 means 5. A person measured it on a measuring stick or on a scale of some sort, and the number came up 5, and that's the number it is. It has a value, and the value is known at 5. All right, well, what about zeros? That is where our main issue comes in. Zeros can play multiple roles, okay? And we'll highlight a few different types of zeros. So, for example, the hardest one, again, we classify these zeros just to help as ways of helping people remember them. But they're just zeros are zeros, you know. The question, does a 0 actually equal 0? And that's the problem. Or does a 0 equal some number that we don't know? Or does a 0 just equal nothing, as in a null value? It doesn't even mean a number, it's just nothing. There's a number of ways in which these zeros can be used. All right. So the first one I'll mention is we call a trailing zero. And again, you may run into things where some teachers handle it differently. I've seen teachers just simplify things more, but this is just for me what works nicely for me. Now, trailing zero, let's say, okay, now the biggest problem, this might be the biggest problem in majority of what we're doing here in this chapter, is the trailing zero. If I have 500 versus, let's say, 500.0, and every kids, if they have an argument about whether something should be significant, I can always throw an example that says, okay, look to get this example. So if I say, for example, an animal weighs 500 pounds. Well, do I mean it weighs, 500 or 500.0? That's a difference. If I say that that little horse weighs 500 pounds, well, then I'm using this as an estimate, where I'm assuming it's not a very accurate value. But if I were to say that an animal or a horse weighs 500.0 pounds, then you automatically assume that I have put this little horse, okay, it's not a very big horse, that I have literally put it on the scale and weighed it, and I am getting its value to literally that number. And this is not 500.0.1, it's 500.0. And all these numbers are actually zeros, where you automatically know that these numbers here, are these actually zeros or are they some other number? So in this case, the 500 decimal working as an estimate, then our zeros kind of follow in this category where it's their numbers are there, we just don't know what they are. And in this one, these zeros work off of this scenario where a zero is actually a zero. So to clarify, just to sort of sum everything up, for trailing zero, anytime I have a zero, regardless, that goes up to the decimal and stops, I treat as an estimate. And I have my point where I lose accuracy as being right here. These are not significant. Okay. Then I have the option of any time I go past that zero, the decimal, then everything is significant and I lose actually right here. So this is sometimes the hardest thing for people to kind of get used to. Is it an estimate or is it not? Okay, so that's a trailing zero. Let's try another example of a zero here. Okay, and in this case we have what's called a trapped zero. Trapped zero might be the easiest one, 5,005. It's a zero between two non-zero numbers, and in reality this number drops off right here in accuracy, and these are significant. Everything this is significant. In this case, a zero actually means zero, just like the 5 means 5. So they are significant. Okay. And the last one we have here is called a leading zero. Okay, now this would be like 0.000055. And in this case, my accuracy drops off here. So I always say that this way is stuff we don't know, and this way is stuff that we do know. Okay, the problem is that these numbers here, they essentially have no value, meaning that they don't mean zero. They do not mean zero. In fact, they mean nothing. They don't mean the number between 1 and -1. They mean nothing. In computer lands, we call that a null value. There's no number that hasn't started yet. And kids will sometimes argue, oh no, that's a perfectly good number. I'm not saying it's not a bad number, but I could literally write this as this, and you could understand what that means, and it would mean the exact same number. Just like I can write 500 like this, and that might be a way that someone would note, okay, I mean 500, but I don't really know what those numbers are. but I wouldn't do this 500 like this, decimal like that. Now again, why would the X be there? Well, someone measured it. Well, what is it? Well, it's an X. No, what is it? This thing now has a value. So this is not, isn't appropriate. In this case, where a number's not significant, you could literally slop an X in there and it really wouldn't change the value. Now, in this case, one example, mathematical example of where this might work. If we take ourselves 55, let's say, millimeters, okay, 55 millimeters, and I'm going to math them out. This thing only has 2 sig figs, and it was determined, this number is measured by some tool, okay. So let's convert this number mathematically with a calculator to, let's say, meters, okay, and micrometers. So for a meter, this thing is going to be 0.00055 meters. And the micrometers is going to be 55,000 micrometers. So in this case, I have not changed my tool, and therefore my accuracy should not change. And by our rules, how many sig figs are here? 2. So I should still have 2 at these points. And do I, by these rules we've just discussed? Yes. Leading zeros do not count. Therefore, these are the significant figures. Okay, here, trailing zeros up to the decimal point would treat this like an estimate of 55,000 micrometers. Are these significant? No. My accuracy drops off right here, and right here. In every case, my accuracy drops off in the same exact spot after the 5. And therefore, 2 sig figs, 2 sig figs, and 2 sig figs. So, in this case, we have leading zeros, trailing zeros, and trap zeros. Things you want to be able to try. And we'll throw some practice examples out here you could possibly try. In this case, a couple other little wrinkles. We have scientific notation. This is something that works very nicely with significant figures. If I have a number like 55,000, all right, and at this point, the way this number is listed, I only have 2 sig figs. So I would write this as 5.5 e to the 4th. These are 2 sig figs in both of these numbers. Whatever numbers I have listed here, they are significant. So let's say, for example, I have 55,000. Okay, and again, I'm being pessimistic by saying my accuracy cuts off right here. But let's say I use a tool that my accuracy actually cut off right here. So the 55000, everything's known, but not the last 0. So again, this is a new idea. This line above here indicates significance. Okay, so that's another way of saying, hey, by the way, these numbers are significant. Even though the standard rules we're using don't show it, this number has 4 sig figs. How would I show this in scientific notation? I would go 5.500 e to the 4th. And I would show all my significant digits in the base unit. Okay. Other than that, you can go the other way around. If I were to have 2.70, let's say, e to the 2nd, let's go e to the 5th. 2.70 e to the 5th. Convert that over, 270, and I would need to have 1, 2, 3, 4, 5. So at this point, what numbers are significant? These are significant. Okay. And that is a little video on how to determine if a number is or is not a significant. Thank you very much.